Thanks a lot, Chairman, and good morning to everybody. I'm from Astronautics, Electric and Energy Engineering Department of University Sapienza on Rome, and I'm going to show you this short presentation, some preliminary results about research on carbon-based ceramic composite materials for high temperature application. Very briefly, the research of the group I work within are related to advanced materials characterization for space and aerospace application, with focus on carbon-based composite technology as well as space environment on-ground simulation. So the aim of the work is the production of high-thickness structures made of carbon-carbon, that is a material realized by the densification by carbon precursor on carbon fiber-based substrates. Such achievement is gained by means of chemical vapor infiltration methods. So after the preform manufacturing, the infiltration process is described, and finally the analysis of the densification result is presented. Just to remind, carbon-carbon materials are widely known for their excellent mechanical properties, almost unchanged at high temperatures such as 2000 degrees and above. By thanks to their lightweight, they are ideal candidates for space high temperature application, like parts of engine as nozzle throat section for launchers. It is another very strategic material that can be so hard and expensive to develop and optimize by the currently employed method, whose the detailed specific know-how is strictly not shared by the main producer corporation. Thus, the aim of this research is to promote low-cost and time-saving process in order to increase the national competitiveness in such framework. So the procedure is followed these simple steps. After the preform manufacturing, 100 infiltration cycles have been carried out with correspondent test as process monitoring. Several preforms, high volume and high thickness, have been handmade in roughly cylindrical hollow shape, with different features in terms of carbon fiber typology and arrangement, with the aim to analyze how such parameters as the woven yarn or the stitching symmetry or the carbon fiber volumetric percentage may affect the effectiveness of densification. Here are the 5 items manufactured, identified by starting each one before the white treatment, and here is the arrangement within the oven before the first cycle. The gas inlet is placed at the bottom, and the gas flow eventually from the hollow core towards the external zone. The chemical vapor infiltration process is based on the decomposition of hydrocarbon molecules at high temperature that results in the precipitation of carbon atoms that are deposited and intercalated between the carbon fiber of the substrate. Thus, the temperature of the reaction, the operating pressure, and the flux rate of the hydrocarbon are the main parameters to be set up and controlled during the whole process in order to avoid sudden environmental change. That is important, particularly for the gradient of pressure between the hollow core and the external zone. This is a picture of some items just after the first cycle of infiltration, and here the first results of the total weight increase. It can be seen that the poor densification occurred for the lowest kappa woven preforms, while the better results are obtained for the top placed preform inside the oven. After the first cycle, one preform was removed for the detailed densification analysis, thus only 4 were put again inside the oven with the same arrangement. And these are the results of the densification after the second cycle that stress again the bad results of obtained for the lowest K oven preform and the maximum value of densification in the highest placed preform. After the chemical vapor infiltration process, the items were cut to obtain a series of roughly cubic shape samples in order to analyze the behavior of the densification along the preform diameter. The evaluation of density may be affected by great error by direct measurement of volume due to lack of homogeneity or macroscopic defects, weaving, etc. Thus, a more precise procedure is needed as the buoyancy method that allows to evaluate apparent density, residual relative porosity, and bulk density only by means of high sensitivity weight measurement that in turn lead to lower values of the error on the volume estimation. And as can be seen by comparing the results of the density obtained by the two methods in the green and the gray column. About the quantitative results, can be stated that the low residual porosity found for the lowest K woven preforms is a signal of the impossibility to reach good values of final densification. Very good uniform bulk density obtained for the preforms placed far from the gas inlet are promising results, while the well-defined radial gradient of density was found for the preforms placed closer to the gas inlet. Such results are stressed again by the full testing of the two remaining preforms, in which a well-uniform densification is found for the farthest preforms from the gas inlet, while the well-defined gradient of radial density is found for the closer preform to the gas inlet. And morphological analysis by scanning electron microscope show the different densification behavior found in lower and higher kappa woven preforms, as well as the different densification between the inner and outer zones in the preform near the gas inlet. And these high magnification in micrographs show the carbon fiber wrapping by the deposited carbon matrix in turbostratic-like fashion. And recalling the total weight measurements, can be seen that the densification occurred in the second cycle is well lower than what occurred in the first one, due of course to the progressive porous obstruction, and again that the lower K values of woven yarn are not indicated in the adopted experimental setup, while the best manufactured preforms placed at the tops of the columnar arrangement inside the oven gives the best results. An heuristic mathematical modelization will be developed in the future by means of further experimental data availability. This model will propose an Arrhenius-like relationship between the overall density and the time of infiltration, depending on the constant time that is related to the kinetic rate of reaction, as well as the dependence of the differential density on the radial position, and to obtain a contact expression depending on 3 experimental parameters. Thus, as concluding, a reliable process chemical vapor infiltration is proposed for high thickness carbon-carbon structures production with high values, relative values of density, while further investigation are needed in order to optimize such procedure. That's